Hey Royals, I've received some questions about lesson 3.3 on solving exponential equations. And it's probably not a surprise. We're using totally different strategies to solve these equations in addition to prerequisite strategies. So I've picked a sample of some of the questions that I've assigned you, and I'm going to go walk through them, maybe show you a couple of different approaches, and try to talk about what's going on in my head as I do these. So our new approach to solving exponential equations doesn't involve, I'm not going to be undoing operations. I'm not going to divide both sides by 4 and then try to get rid of the base of 2. I'm not going to set equal to 0 and try to solve by factoring or using the quadratic formula. I'm going to try to write both sides as a single power of a common base. One of the concerns that came up was that sometimes students feel like they're doing a little bit of trial and error here, and that's healthy. You shouldn't be substituting in values of x trying to find the answer to this question, but there will be a little bit of trial and error going on here. Okay, the first question, I mentioned I'm not going to solve it, or I wasn't going to solve it by trying to isolate, but I can actually undo this operation if I like. The left-hand side is not a single power. These are two powers that are being multiplied together. One of the ways of writing this as a single power is to undo the multiplication by 4 with an inverse operation. I can divide by 4 on the left side if I divide by 4 on the right-hand side. When I have 4 times 2 to the exponent x divided by 4, there's no distribution here because it's a product. The 4 divided by the 4 will give me 1. And 1 multiplied by 2 to the exponent x is 2 to the exponent x. That's a single power. It's a single power. On the right-hand side, 32 divided by 4 would be 8. And I might just be able to see the answer to this question, but I want to practice the skills that I'm recommending. I'm now going to try to write both sides as a single power of a common base. Both sides are a single power. This is 2 to the exponent x. This is 8 to the exponent 1. I'm looking for a common base. And usually, when you're looking for strategies for finding a common base, you could try the smallest number, the smallest base. That's not always a great approach, but it's a decent place to start. In this case, I can, but I don't want to write 2 as a power of 8. It's 8 to the exponent 1/3, by the way, but I don't think that's an intuitive approach. Instead, I think most people would see, oh, I can write the left-hand side as a power of 2. It already is a power of 2. And I can write the right-hand side as a power of 2. Now, if you're not familiar with the powers of 2, then this will require a little bit of trial and error. You're saying, is 8 a power of 2? Well, let's see, 2 to the exponent 1 is 2, to the exponent 2 is 4, to the exponent 3 is 8. So I have, through trials, I suppose, discovered that 8 is 2 cubed. But I hope we get comfortable with our powers of 2. This is where the communication comes in. You have the left-hand side being a power of 2 and the right-hand side being a power of 2, and your powers are equal. That means that your exponents must be equal. This is not a mathematical step that we're taking right now. We are not dividing both sides by 2. We're just saying 2 to the exponent something equals 2 to the exponent 3. That means that something has to equal 3. Okay, let's try 6c. 6c looks a little different. It has 125 to the exponent x equals 25 times the square root of 5. Oh, shoot, I wanted to try 4 in another approach. Let me just do that off on the side here. This second approach might look a little bit more familiar when we look at 6c here. So I might notice when I see these expressions, I notice that there are 2 powers on the left-hand side. I could write both of these powers as a power of 2. 4 is 2 squared, I recognize that. 32 is 2 to the exponent 5. I think I've just memorized that. It used to take me a while to get my powers of 2 down. I think 2 to the exponent 6 being 64 was a good memorization point for me because it starts with a 6, and then this is just going to be 1/2 of whatever 64 is. Just be very careful here. You're not you're not ready to set your exponents equal to each other, or even write an equation about your exponents equal to each other. You really want to show your reader both sides written as a single power. So use your power laws from grade 9 right here to multiply two powers with the same base. You keep your base and you add your exponents. If you have x factors of 2 and then you multiply by 2 more factors of 2, you now have 2 plus x factors of 2. And if 2 to the exponent 2 plus x is equal to 2 to the exponent 5, that means that 2 plus x has to equal 5. And notice that now I have a linear equation that I can solve by isolation. And I should get the same solution, the same answer, I suppose. Okay. That might have been helpful in doing 6C, because in 6C, you can divide both sides by 25, but it's probably not going to do what you want it to do. 125 to the exponent x divided by 25 is not 5 to the exponent x. This is not how you work with powers. If you have 4 to the exponent 3 divided by 2, that's not just 2 to the exponent 3. This is 64 divided by 2. 64 divided by 2 is not 8. And these are two powers with different bases. We will pretend we don't have properties for those. So I'm going to notice that all of this is a multiplication, and I know some power laws for multiplication. So I think I'm going to start by trying to write both sides as powers of a common base. My common base in this case, again, I'm going to try with the smallest base. Maybe I didn't know it right away that 125 is a power of 5, but if I use a little bit of trial and error, I think I will be able to write 125 as a power of 5. My powers of 5 are, 1, 5, 25. And what's the third power of 5? Well, that would be 25 multiplied by 5. If I have 5 quarters, that's a $1.25. Okay. So a little bit of trial and error. You don't need to show that work on the side here. Let's just show that 125 is 5 to the exponent 3. That is now raised to the exponent x. Notice I'm replacing 125 with 5 cubed. That requires a bracket now. 25 is 5 squared. And the square root of 5 is 5 to the exponent 1/2. Review your rational exponents if you have to. The left side is not a power of 5 yet. The right-hand side is not a single power yet. So take some time and tidy up here. On the left-hand side, to simplify the power of the power, I'll keep my base and multiply my exponents. On the right-hand side, to simplify the product of two powers with the same base, I can keep my base and add my exponents. 2 plus 1/2 is going to be 2.5, also known as 5 halves. Okay, this is 4 halves plus 1/2, 5 halves. Now that I have both sides written as a single power of a common base, I can argue that since my bases are going to be positive in this course, my exponents have to be equal. There are some weird restrictions when your denominator is, when your base is negative that we don't need to worry about. Let's try avoiding a division by 3 here, because I don't want to write 5 over 2 over 3. Let's multiply by 1/3 instead of dividing by 3. And that'll give me that x is going to be 5/6. This is why you don't want to use trial and error on the original line, because I don't think I would ever try the exponent 5/6. But if you're using a little bit of trial and error to figure out your common base and how to write 125 as a power of 5, even your calculator can help you out there. That's okay. That's what's required of us for right now. Okay. Let's try 8E. Looks a little bit like a lesson example, but to me, this is maybe the most important type of question when you have mixed strategies. Okay. So in 8E, 2 to the exponent 2x plus 2 plus 7 equals 71. I could start off with a couple of concerns. If I just try jumping right into my strategy of writing both sides as a single power of a common base, 7's a prime number. I don't think 7 can be written easily as a power of 2. I think 71 is prime as well. It's definitely not a multiple of 2, so it can't be a power of 2. The next problem, even if this were, say, 8 here and this were, I don't know, 64, is that I don't have a rule for adding powers with the same base. Okay. Often in a test or in a quiz, students will come up and say, oh, I can't remember what the rule is. And you know how I feel about memorization versus understanding. the reason why you might not remember what the rule is maybe there isn't a rule. No, what I'm going to do is instead, the left-hand side is not a single power, it's a sum. I can treat this more as a linear equation, though. If I want to undo an addition by 7, that can be done easily in this question with an inverse operation. I might be looking a step ahead and a little worried about what's going to happen here. Let me just calm myself down and simplify first. If I do 71 minus 7, that's going to be 6 less than 70. That's going to be 64. Well, guess what? 64 can be written as a power of 2. A common question here might be, well, what if this wasn't? What if this was 63? That's not a question for this course. That's a question for advanced functions. And if you're getting frustrated with solving exponential equations and you're doing a little bit of research on your own, you might come across something called a logarithm. Please stay away from those. You won't be expected to use them, and it's not an easy tool to use if you don't understand how it works. 64. Let's talk about our powers of 2. 2 to the exponent 1, 2 to the exponent 2, 2 to the exponent 3, 2 to the exponent 4, 2 to the exponent 5, 2 to the exponent 6. It's just doubling in my head. If you think that that's trial and error, then I think it's a more organized and more informed type of trial and error than, say, just trying to guess what the answer to the question is. Now that I have both sides written as a single power of a common base, I argue the exponents must be equal. So I go from using a linear approach, undoing an operation, to solving in an exponential approach, trying to write both sides as a single power of a common base, to when I equate my exponents, solving as a linear equation again. I now want to isolate x. I'm not going to write both sides as a single power of a common base because this is not an exponential equation. It doesn't have an unknown in an exponent spot. I am going to solve by isolating, by undoing operations with inverse operations. If I want to do a quick informal check here, I might have been able to spot this solution. The double of 2 is 4, plus 2 is 6, 2 to the exponent 6 is 64, plus 7 is 71. But that's not how I want you to solve these. Let's try one more. 9h. 9h starts off with 9 to the exponent x squared plus 1 equals 27 to the exponent x multiplied by 3 to the exponent, I think that's a 2x. Okay. We've got a multiplication on the right-hand side. That's usually good news. That means that there are some properties that I can use, but I don't know what the rule is to multiply two powers with different bases. I know that, for example, if I have m factors of b and then I multiply by n more factors of b, that makes sense when I think about it and I read it in English, that I will have m plus n factors of b. But what if I have, I don't know, like 2 factors of a and I multiply by 3 factors of b? I can't simplify this at all. Right, there's if I can't remember what the rule is, again, I don't think I should be concentrating on memorizing, but maybe it's because there isn't a rule. 9, 27, and 3, they're all multiples of 3. I'm not looking for multiples of 3, though. I am looking for powers of 3. If I use a little bit of trial and error and look at my powers of 3, the first power of 3 is 3, the second power of 3 is 9, the third power of 3 would be 9 times 3. That's 27. There we go. Okay, be careful. If the question looked like this, 27 is a multiple of 9. It's 3 times 9, but 27 isn't an integer power of 9. 9 to the exponent 1 is 9. 9 to the exponent 2 is 27. Often students mistake multiplication with exponents, probably because they were taught that exponents cause repeated multiplication. Okay, so I think I've decided that my common base is going to be 3. Let me do this time. What I'm going to do is I'm just going to put a bracket around where every other base used to be. I'm also going to upgrade these brackets here. That's already a base of 3, so it's ready to go. Okay. Now, when I see 9, I write 9 as a power of 3. It is the second power of 3. I see 27, I write that as a power of 3. It is the third power of 3. I have a common base, but this is not a power of 3 right now. It's a power of 3 squared. This is not a power of 3 right now. It's a power of 3 cubed. And the right-hand side is not a single power. So I've got some work to do. On the left-hand side, I have a power of a power. I'll keep my base and multiply my exponents. If you haven't been doing this, get used to performing operations in the exponent spot. Often students, they're not used to having done operations. I hope you had the chance in grade 9 to do operations in the exponent spot. But I know some grade 9 students just always do this operation off to the side because they feel like they can't do work in the exponent. You can and you should. Here, I'll keep my base and multiply my exponents. Here, I already have this is some artwork by my 2-year-old son getting in the way here. I'm just going to write right over it. That's how much it means to me. 3 to the exponent, 2x squared plus 2 equals, on the right-hand side, I have 2 powers now with the same base that are being multiplied. And to simplify the product of 2 powers with the same base, I can keep my base and add my exponents. All right. Now that I have both sides written as a single power of a common base, I am going to equate my exponents. So I'm done with the exponential nature of the question now, and I reevaluate, and I notice that I am looking at a quadratic equation. Solving quadratic equations cause some problems for some students in this course. Solving quadratic equations efficiently caused more problems for students in this course. You are not going to be subtracting 2 from both sides and then dividing by 2x to isolate x. You'll have an instance of x there. This is a quadratic equation. I'm going to solve this quadratic equation by, there's the possibility of trying to isolate for x by completing the square. I don't like this option right now because I would have a fractional coefficient there. So let's set it equal to 0 and try using our other approaches. Want to say hi?
Hi.
That's my daughter. Okay. The quadratic formula should work, but I think it's worthwhile to try factoring. In fact, I might even see the option of getting a 4 and a 1 here if both of my signs are negative. No. Let's see, I'm looking for the -4 minus 1, like that. So up here, I will go 2x with the -1 multiplied by an x minus 2 equals 0, and I will always check with distribution because there's really no, I mean, you can make a mistake, but if there's a way of catching your mistakes, there's not much of an excuse for making a mistake when you factor. Quadratic formula is a lot harder to catch those mistakes. 2x squared minus 4x minus 1x, that's minus 5x plus 2, looks good. So this means if a product of 2 factors is equal to 0, then either the first factor is 0 or the second factor is 0. This is another one of those, I think, really interesting equations where you go from being an exponential equation to a quadratic equation to 2 linear equations. And you shift gears on every approach. You don't try factoring here. You try to write both sides as a single power of a common base. You don't try isolating for x here. It's a bad idea. It could work if you really like completing the square. I don't get the idea that any of you do. Here, you could solve this by factoring. You could, I'm not sure how else you're going to solve. You could isolate. 2x is equal to 1, or x is equal to 1/2, or x is equal to 2. I'll let you check those answers on your own. It's kind of interesting how this works. That because of the squared exponent here, you end up having quadratic solutions for your exponents. Okay. Now just keep in mind on the outline, I did point out that I think questions 23 and maybe there's another one somewhere on the list, question 24, yeah, are considered extension. Okay. Let me know if there are any other specific questions from there that you want to practice. It is a really important lesson because it's a new type of solving and it takes some practice to get used to, but I'm sure you can handle it.